After this lesson, I hope you'll have a good understanding of two physics concepts that are often confused: heat and temperature. Here's young Francisco with a fireworks sparkler. The sparks are high temperature, quite hot. But if the sparks hit his face, not a problem. Here's John walking barefoot on red-hot coals. Again, high temperature, and without harm. More on sparklers and firewalking later in this lesson. These feats, whether encountering high-temperature sparks or high-temperature coals, lead us to making a distinction between heat and temperature. Let's define temperature. We know that all matter, solids, liquids, or gases, is composed of continuously jiggling atoms or molecules. We'll say particles to mean either atoms or molecules. The particles are in random motion. The average kinetic energy of individual particles produces an effect we can sense: warmth. Temperature. The kinetic energy of particles in a substance can be of several modes. Particles may move from place to place, which is translational motion, the motion that contributes to temperature. They may also undergo rotational motion, or they may vibrate to and fro, vibrational motion. All these modes contribute to the overall energy of a substance, commonly called thermal energy. The word thermal is from the Greek term for heat. Physicists, however, prefer the term internal energy. Internal energy is the sum total of all particle energies within a substance, measured in joules. Getting back to temperature, translational motion and its corresponding translational kinetic energy is what defines temperature. Temperature is a measure of the average translational kinetic energy per particle in a substance. Rotational and vibratory motion may be energetic, but they don't contribute to temperature. It's translational motion that contributes to temperature. Whereas energy is measured in joules, temperature is measured in degrees. Temperature is expressed by degrees of hotness or coldness on some chosen scale. Two common scales are the Celsius and Fahrenheit scales. Your textbook tells of the origin of these scales, both interesting stories. The temperature of melting ice on the Fahrenheit scale is 32 degrees, and on the Celsius scale, 0 degrees. The temperature of boiling water at atmospheric pressure is 212 degrees on the Fahrenheit scale and 100 degrees on the Celsius scale. Then there's the less common Kelvin scale, which we show side by side with the Fahrenheit and Celsius scales. We call this the absolute temperature scale, which treats temperatures as low as absolute zero, the bottom of what's possible in temperatures. When a substance has given up all of its available energy, we say that the temperature of that substance is absolute zero, or 0 kelvins. Cold, really cold. That's 273.15 degrees below zero on the Celsius scale. We'll return to the absolute scale in a follow-up lesson. Converting from one scale to the other is an exercise in arithmetic, but nevertheless has consumed lots of time in some physics classes. I don't see the physics of it any more than in the joke question, who is the Celsius scale named after? I quip that the answer is Anders' scale, just as Washington Street is named after George Street. Not much physics in either the arithmetic conversion or the joke questions. Now for heat. If your tongue touches a piece of hot apple pie, energy transfers from the hot pie to your tongue. If you touch a nail stuck in a piece of ice, energy transfers from your hand into the colder ice. Here's a key point. The direction of spontaneous energy transfer is always from a warmer object to a neighboring, cooler one. We know that matter contains energy, which can be in various forms. All forms together comprise the internal energy in a substance. But matter does not contain heat. Heat is energy in transit, from an object of higher temperature to one of lower temperature. Once energy is transferred, it ceases to be heat. An analogy is work. which is also energy in transit. Things contain energy but not work. An object does not contain work. Rather, it does work or has work done on it. How much heat flows depends not only on the temperature difference between substances, but on the amount of material as well. Consider these containers on a hot stove. You'll see the temperature increase more in the left one. Why? Because there's less water to be heated. We'll treat heat transfer in a future lesson. Let's get back to our fireworks sparkler. The temperature of the sparks is greater than 1,000 degrees Celsius. That's a lot of energy per molecule of spark. But the relatively few molecules per spark translates into a relatively small amount of energy. Temperature is one thing, transfer of energy, heat, is another. Let's return to firewalking. As with a high-temperature sparkler, the amount of energy transferred from the hot coals to John's feet is relatively low. As long as he steps quickly, very little energy from each coal transfers to his feet. This involves thermal conductivity, which we'll cover in another lesson. As said, know that temperature is one thing and heat, transfer of energy, is another. Very different. In learning physics, please be patient with yourself if you're overwhelmed a bit from time to time. Acquiring physics knowledge is akin to acquiring knowledge of many kinds. The skill that comes with being a musician, for example, is not acquired overnight. It takes time, sometimes a lot of time, and patience. Rome wasn't built in a day. Here we see Kelvin and Celsius temperature scales side by side. The Celsius temperature is 10 degrees, which on the Kelvin scale, the absolute temperature scale, is 283 kelvins. 10 degrees Celsius is the same as 283 kelvins. We say kelvins rather than degrees for the absolute scale. The absolute zero mark would be at the bottom of this page. Let's suppose the temperature reading is for this iron bar. We know that the temperature of the bar is proportional to the average kinetic energy of its iron atoms. If we apply heat to the bar, the kinetic energies of its atoms increase. If we apply enough heat to the bar and increase the average kinetic energy of its atoms by twice, it will be twice as hot. On the Kelvin scale, this would be twice 283, or 566 kelvins. Let me leave you with a question. What will the temperature be of the twice as hot bar in Celsius degrees? Until next time, good translational kinetic energy.